Good morning, everyone. I am happy to talk to you this morning on the genetic and functional studies of Still syndrome and its implications for public health. As a background, Still syndrome is an autosomal recessive orthopedic syndrome that was originally described in 1993 by Dr. Still by observing children from Puerto Rican ancestry that shared features of short stature, bilateral congenital hip dislocations, carpal coalitions, dislocated radial heads, foot deformities, scoliosis, cervical spine anomalies, and some abnormal facial features. However, the gene responsible for this disorder hadn't been identified until in 2013 when we performed as part of the Centers for Mendelian Genomics at Baylor College of Medicine, we performed exome sequencing of a family from Puerto Rico with 2 affected children and a reportedly affected cousin. And we identified through analysis of the exome sequencing data, homozygous missense rare variant in the gene called 27A1, shared by all the affected individuals. However, as I mentioned, this variant, although was in homozygosis in all the affected individuals, we didn't find any evidence of parental consanguinity consistent with self-reported lack of relatedness among the parents for these children. Therefore, at that time, we proposed that this variant in COL27A1 was a founder mutation that had occurred in the Puerto Rican population and that was segregating in this population, causing Still syndrome. However, at that time, when we published our study in 2015, we didn't know what was the functional effect of the variant. We hypothesized that this was loss of function or a hypomorph allele, and we also didn't know the prevalence of the disorder in Puerto Ricans or the variant, the frequency for the variant in this population. Since then, we set out to develop an in vivo mouse model of the variant of Still syndrome to figure out the functional effect of the allele and further understand the disorder. And therefore, we developed a knock-in mouse model with the orthologous variant in the COL27A1 mouse gene. As similar to the observations in human, the heterozygous mice were normal. However, we were able to recapitulate some of the features observed in Still syndrome patients in the homozygous knock-in mice. For example, we were able to see that the homozygous knock-in mice were smaller. They had reduced length, which is similar to the short stature observed in the human patients. They also have thoracic kyphosis, which is similar to the spinal abnormalities observed in the patients. And they also had varus deformity in their hind limbs. And also they had a more rounded skull that you can see here through these tomography images, where you can see the tongue protruding due to the shortening of the snout in the homozygous knock-in mice and this more rounded skull structure. Additionally, we performed histology in the long bones of these mice. And as you can see here, the wild type and the heterozygous mice have similar lengths of the long bones. So the growth plate of these mice is preserved, while in the homozygous knock-in, the growth plate of the mice is collapsed due to loss of the proliferative zone of the chondrocytes. And also we see disorganization of the columnar chondrocytes in the hypertrophic areas of the growth plate in these mice. So in summary, through genetic and functional studies, we were able to define that Still syndrome is a clear clinical and molecular autosomal recessive disorder characterized by short stature, bilateral hip dislocations, carpal coalitions, scoliosis, cervical anomalies, and it is molecularly caused by the glycine 697-2-arginine variant in the gene called 27A1. And therefore, we propose a molecularly guided definition of disease for this disorder. We were able to confirm homozygosis for this particular variant in some of the original Still syndrome families identified by Dr. Still through collaboration with Puerto Rican collaborators. We were also able to narrow the common haplotype harboring this STLS variant to a 2.6 megabase region in chromosome 9. And it has been estimated that the carrier frequency for this allele is about 1 in 51 Puerto Rican individuals, which is relevant for neonatal testing and counseling for families in Puerto Rico about this disorder. So this is an example of how genomic sequencing of uncharacterized population cohorts can provide insights to novel disease genes that may be enriched in these populations due to mechanisms such as genetic drift and consanguinity, and estimate the prevalence of rare genetic disorders that may be more common in these populations, providing opportunities for early diagnosis and treatment options, which has implications for public health, screening, and prevention. And with that, I'll thank all my collaborators, and I'll be happy to take questions. Thank you.